Looking at 1.2 basic classes of functions, and we know that a relation is an algebraic relation between two variables, and a function is a relation such that each element of the domain is paired exactly one element of the range. And we went over some of the facts with linear functions. I just want to recap this. About a graph is a line with a constant rate of change, and it's a polynomial degree 1. And if we look at a couple things, we know that we have a negative slope and a positive slope. If I can write this here real quickly, and just thinking about if I have a line that is such as y is equal to a negative slope negative 2x plus 5, we know that the line is going to be decreasing, or it's falling from left to right, versus a positive slope. I'm going to write it like this: y plus 3 equals a positive slope of, I'm just going to make it 1/3, and then x minus 1. So with the first one, we know that the slope is negative 2, and the y-intercept, of course, is 5. And the second one, we know that a point on the graph is 1, negative 3, and so let's say the slope is equal to 1/3 in that point slope form, and you see those two forms above, okay? So just going over this very briefly as you see our linear graph. Then we have quadratic functions. It's that U-shaped graph. So we talked about that, where it's a polynomial degree 2. The curve is either concave up or concave down. The standard form and the factored form is given there. And A, B, and C are different letters, are not the same for both of those expressions. But that's the way the setup would look. And then the vertex form, where we have the center, or I'm sorry, not the center, but the vertex is HK. And for this one, we're talking about y is equal to x squared. We're talking about end behavior, so I'm using the model y is equal to x squared there, and I'm saying as x goes to infinity, y goes to infinity, and so on and so forth. And that seems to be a pretty good topic with you guys. But the domain we write in interval notation, and I didn't talk about that so much up there. It's kind of very similar here. But the negative infinity to infinity, we don't include infinity, so that means we're using the curved parenthesis versus the bracket. You have the bracket meaning that we are including the 0, and it's heading off to infinity in terms of the range. The range, remember, is the y, and the domain is the x. Okay, so I could say I would have y is equal to the quantity x minus 2 squared plus 3, and then we would say that the vertex in that case is then going to be 2, 3. Okay, and I could say something like y is equal to negative x squared minus, we'll do a plus 5, it doesn't really matter. And so then we have the vertex for this one. Remember, it's just the x by itself is then going to be 0, 5. It's just going to be negative x squared, and it's going to go up. So where you're going to be here, you're at 2, 3 for the vertex. And it's going to go upward because a is 1 in this case. And here a is negative 1, so we know we're going to be upside down. And we're going to be here on the y-axis is 0, 5, and it's going to head down. Okay, both dilation factors are such that you're going to start at the vertex and go over 1, down 1, over 1, down 1. The same thing with the first example that I gave you. With the first example, you're going to have that movement of over 1, up 1, over 1, up 1. Okay, then you have the cubic graph that we talked about. So you have y is equal to x cubed. We know that it's kind of like you're putting two graphs together. Over the right of the y-axis, your graph is concave up, and on the left of the y-axis, your graph becomes concave down. And so there is what we call a point of inflection at the origin on this graph. And I skipped the factored form there because it depends on whether it will factor or not, but there is a factoring form for a cubic, or there's a way to find the zeros, but we're not going to get into that. And we have the domain and range are given there, all real numbers. And then you have the end behavior of the graphs that you need to be aware of. Okay, you can stop the video at any time and kind of review this if you're not quite sure. You have an exponential variety where you have exponential functions. Y is equal to 2 to the x as the example, simple example, where you have a horizontal asymptote. Let me do it a different color. So we've got a horizontal asymptote along the x-axis. That's y is equal to 0. So if we know that a is greater than 0 in both cases here, a is greater than 0 and b is greater than 1, the first case we know that we have a growth, and then we have a decay if b is between 0 and 1. Now there's some flipping that might involve like a reflection over the x-axis at times, or the y-axis for that matter, but we're not dealing with that right here. And then the end behavior of y equals to the x, you see that we have that horizontal asymptote y is equal to 0, so as x goes to infinity, y goes up to infinity there. infinity. And then as x goes to negative infinity out this way, that you can see that the y goes to 0, okay? And I have a little table there if you need to stop that and look at negative exponents. If I replaced x with negative x, then you would end up with a base of 1/2 x, showing you the decay. It's actually, I'm going to quickly undo this, but it's going to look something like this. It's going to sweep downward, okay? And it's going to have like kind of the opposite effect with the horizontal asymptote. Okay, and be careful with those negative exponents. Then you have the logarithmic function, which we didn't get to, but we're going over it very quickly here. One of the ways to look at it is x is equal to 2 to the y, and if I did a table of values for that, I would put input y and then output x here for ease in trying to figure out what you're doing, if you're doing it by hand. And so taking this, x is equal to 2y, then I would put in 2 for y, 0 for y, and negative 2 for y. And I would get the following values. I would get 4. I would get, so 2 to the second power is, of course, 4. 2 to the 0 power is 1. You see the 0.10. And then you have 2 to the negative 2 power, which is going to be 1/4. And you can see the points that we get there for x and y on the graph. And then you have your end behavior of the graph and your domain and range. Remember, you cannot take the logarithm of a negative number. And the same thing is true, though you have log base 10 of x. When you see that, remember that it's log of x. And if you have log base e of x, we write that as ln of x, and those are familiar in your. So we call that a common logarithm. That's a natural logarithm here. Y is equal to ln of x. Okay, just different ways that we can write that. But it's so commonly used that we just have a simplified version of that. Rational functions, then we have, and we did this where both the numerator and the denominator are polynomials. So you have this r of x rational function where it's p of x over q of x. And it could be a polynomial or a constant in there to make it a rational function. So we have these three rules. If the degree of the numerator is less than the degree of the denominator, you have a horizontal asymptote at 0. So if we look at this, I'm looking at g. So the horizontal asymptote for this one, because the degree of the numerator, the degree is 1, and here in the denominator, the degree is 2. So that fits your first case there, where the horizontal asymptote is y is equal to 0. Much like the one that you see here, it's the y-axis. Okay. Then you have the second one, the second case, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. So I would look at these, and I would often take a second and say, okay, these are the boss terms, so to speak, of the numerator and the denominator. So I would say, okay, the horizontal asymptote here for this case is y is equal to, I'm just going to write it as 3x over 2x, but then we would simplify it to y is equal to 3 over 2. So that would be the horizontal asymptote for that first example I gave. And for the last one, I didn't do that here, the degree is 1. The degree is equal 1, and here the degree of the denominator is also 1. Okay, both the same. In this one, we can say the degree is 2, and then the degree is 1. So the degree of the numerator is greater in that case, so there would be no horizontal asymptote. Okay. Moving along, you can pause this if you like and kind of go over those facts, fill in the rest of your notes. And then you have the absolute value function. And I just want to remind you that the absolute value of x is equal to x, right here, when x is greater than or equal to 0, and it's equal to the opposite of x. Notice I said opposite of x, because sometimes it's confusing for students when you say the negative of x, because they're thinking, oh, absolute value is never negative. But in this case, you have to be careful because it's the opposite. So we have our absolute value graph, absolute value form, then as a complete expression would be y is equal to a times the absolute value of x minus c. I'm going to put h there, sorry, minus h. And then we could also have a plus k. So there's a multiplying possibility out front with the a, multiplying factor. It's for a dilation, stretching and shrinking. And then there's the minus h, which would go left or right, and the plus k would cause it to go up and down. As x goes to infinity, you're heading out here, it looks like you're going to infinity. And as x goes to negative infinity, it looks like you're also going to infinity with this particular graph. And the domain would be from negative infinity to infinity. Oops, turn my paint off. Okay, negative infinity to infinity, and the range would be from 0, but we're including 0, and it goes upward to infinity, okay? Just a little note about this. When you look at the example that we have, the opposite of x minus 3, it just matches this definition perfectly, except it's not x, it's x minus 3. So we have to know, where is x minus 3 equal to 0? And to the right of 3, you're going to have a positive expression. To the left of 3, you're going to have a negative expression. So where 3 is, that's where x minus 3 is equal to 0. You go left and right and determine which one is positive, which one's negative. And the one that turns out to be positive is when x is greater than or equal to 3. So it's the same expression that's on the inside. Okay, and then we have square roots. So we have the square root. There you have your form. You have your dilation factor. You have your shifting left to right with that h, x minus h. And if h is negative, you're going to the left. If h is positive, then you're going to the right. Then you have the parabola, is the name we call it. It looks like a sideways parabola, but it's only the top half, where the bottom half would be like this, okay? And then you have the domain. Also that this can be written as exponents, 1 over 2. So we have the square root where that little index is right there. It's a 2, and then there is x to the first power, so we can switch those in the order, and we have x to the 1/2 power is what we have. Okay, and then we have the end behavior. As x goes to infinity, the graph is going to continue to increase, and as x goes to 0, y goes to 0. The domain, of course, is x is greater than or equal to 0. You have the domain here, and then the range is also the same way, because you start here and you go up. So you start here and you go over for x, and then y. You can, of course, continue to increase. Remember, when you write the interval notation, you're going from low to high. Now, I could do the same thing here, but in the interest of time, I'm sure that you can look at functions that look like this. Y is equal to 2 times the square root of x minus 3 and minus 2. To see that that is the square root function dilated by a factor of 2, stretched by a factor of 2, and then shifted 3 units to the right and 2 down. Okay, so just to be able to look to see what other translations that you can apply to the square root function. Then you have this greatest integer function. So one thing I wanted to say about that is when you input x into the greatest integer function, I gave you 2 very simple charts there to look at, that if x is negative, it's the greatest integer, not greater than x. So in the first case, when x is equal to negative 1.5, the integer, you just go to the integer below, just below that value of x. When it's not an integer, when it's a decimal, then you go to the integer just below the value they get. And I'll read the definition then. And this is the same thing over here. When x is 1.5, you go to the integer below 1.5, which is 1. So when you take the greatest integer not greater than 1.5, it's going to be just below 1.5 or 1. And then just below negative 1.5 or negative 2. So when you do this and you pick your values, you can see that what you're going to get is when you take the greatest integer function of an integer, you get that integer. So it returns an integer value for each specific interval. So you notice these are steps, so it's very often called a step function. So if x is a decimal, you round down to the nearest integer below. So another example is negative 3.759. You get negative 4 for a value. Then as x goes to infinity, y also goes to infinity, but this is not a continuous graph. It's discontinuous. But it makes sense, and there's some practical applications for this very much with shipping. Sometimes they charge you, and I'll just say some random values, they charge you $20 for a box between 10 and 15 pounds. They may charge you $25 for a box between 20 and 25 pounds. So those intervals are the same idea here, that between 20 and 25 pounds, all those values, then they're going to charge you $20 or $25, whatever I said. Okay, and then it jumps up to the next step, so to speak. Then you have trig functions. I believe we talked about these a little bit, but sine x and cosine x and tangent x are the most common ones. And so I have some information there about that. You'll remember that from a trigonometry class that you had at some point. And remember that the a, b, and c, and d are constants, and they cause the function to behave in different ways, where the period of the function, if you look here, is 2 pi over b. The amplitude is the a out in front. That controls how high and low you're going to go from the midline, and the midline in this case with the sine x is the x-axis. Okay, and then I also have the tangent in there. And remember that you often want an expression for the domain or the vertical asymptotes of a given function that's discontinuous. And so you have the domain and range here for sine and cosine, which oscillates between the high and the low, in this case, -1 and 1. But with a tangent function, the range is from negative infinity to infinity. It keeps going, but the breaks in the graph occur for the tangent function. When x is pi over 2 and negative pi over 2. So notice I just put a plus here, but if I add pi, I get to the next asymptote. So the domain is going to restrict all those values of x. Okay, then you have polar graphs, and with polar graphs, and I'll let you look at this, but we can come back to this if you have any questions about it. But what we're doing is we're looking at the fact that unlike Cartesian coordinates, we have r theta points where r is the radius and theta is the angle. So a standard function has the form, in this case, r is equal to a sine theta, where a is a constant, r, a, and theta are constants, or, well, r and theta are variables, but the constants, the r and the a and the theta, yeah, I have to change that because a is a constant. A is a constant, but I wouldn't say they're variables, so to speak, but they're not constants. The variables are r and theta. A is a constant given the specific function. And what we often want to do is go from polar to rectangular and rectangular to polar. So if we had, say, for instance, this particular function, I would say, well, x has to be equal to r cosine theta. So, and y is equal to r sine theta. I would use those formulas. And I'm going to be brief with this in the interest of time. But if I want to change from polar to rectangular, I would have those formulas, and we can go back and forth. And I'll hold on this. Maybe I'll have time to do something tonight on that. All right, and then you have the parametric equations too. We won't get into those just yet, but you can see that what's nice about parametric equations is, say, for instance, x will control some kind of horizontal behavior of a graph, and y would control a vertical behavior of the graph. And two things that are moving with respect to a third variable called, say, time. And so t is known as the parameter that controls the movement of the x and y. And sometimes you want to focus in on maybe the horizontal behavior and see and compare that and watch that. And so we can go from parametric to rectangular, and you can see that combining the two equations, we would do that through a system of equations. And we solve for the parameter t, and then we back substitute to get this equation that you see, 1/4 x squared. Okay, so you can see when I inputted up top, you can see that I have specific values of t that I'm using, like as if I would start. So if I start at t equals 0, you can see the direction goes to the right then. I get an x0 and a y0, and then t equals 1 second later, I'm at x is equal to 2 and y is equal to 1. And then when t is equal to 2, I have x is equal to 4, y is equal to 4. And then I just stop there. I was just kind of bored. But then I go to the left-hand side and I go, all right, what if we went back 4 seconds in time? 2 seconds in time. Then I would be at -4, 4, and then I would be at -2, 1, and then I would be back at the origin, and I would continue to move in that direction. So it's behavior of a graph that is controlled with that the parameter t when you draw it, and it's not just x and y, okay? All right, so that's it for this video. I'm going to think that you can take this and you can stop at any point and kind of review what you need to if you have any questions, okay? And have a great day, and I'll see you when I see you.